Okay, so 2.2, in this entire chapter of chapter 2, we're going to be learning a lot of different techniques, okay? So chapter 2 will cover many different techniques for solving first order differential equations. Okay. So we are going to focus on first order differential equations. The later we get into the course, we'll move on to second order and higher order differential equations. But first order, having a really good foundation in this is very valuable in any class that you might take in the future. But also that idea of practicing the decision making, I think, makes learning new strategies more accessible. So we're going to start with separable equations. Now, what we know, what do solutions look like? This will be in that 2.1 video that you're going to take a look at, okay? Things that we used to know at some point. Like, I know you learned these things at some point because you had to know them to get here, but they might be just a little bit, you know, somewhere in the back of the brain right now, and we want to bring them a little bit closer to the front of the brain. All right, so basic integration formulas like power rule, things like that. Integration by parts, integration using partial fractions, and I'm actually going to throw U sub in here as a basic integration formula, okay? And so if those things seem very unfamiliar to you, I would recommend going to an internet resource of your choice. I like Paul's online notes because he has a really comprehensive section for Calc 1, Calc 2, Calc 3, and you all are in luck, differential equations. Okay, so if you haven't checked him out in a while, but you used him for calculus, I would say that some people don't really like it in the beginning because it's not a video-based platform, but I find the way that he writes things to actually be very, very easy to read, easier than a lot of math textbooks out there. So if you've never checked out Paul's online notes, I might Google that right now, bookmark that, but he's got a lot of great examples. And he shows so many steps, like he shows a lot of steps to help you connect the dots, okay? So if any of these integration things seem unfamiliar, check out Paul's online notes. He is some random professor in Texas. I think I figured out he worked for a school in Texas. And he's a professor, and he puts up all of his notes and practice problems for anyone to use. It is a completely free resource. I don't know that who he is exactly, but I know that he is an amazing contributor of resources to technology, to calculus. All right. I would like to meet him personally. I feel like he's done so much good work, and we all use his stuff so much. But anyway, I digress. What's new? So we are going to learn how to algebraically solve one type of differential equation. Okay, so in particular, today we are looking at separable differential equations. Tomorrow we will look at a different kind. And so as we move through, it would be really important to think about when can you use this method and how do you know? All right, so not just how to do it, but when do you use it? That is the trickiest part, okay? So without further ado, let's move on to the concept. So the way I'm going to try and frame this, we're going to go through examples, but before we get to the examples, I would like to figure out how this technique works. And so what we're going to do is we're going to sort of use a general way to figure out how things work using a lot of symbols, okay? And then we will do examples with numbers, okay? One of the things I know about differential equations is that because if you take like the next course up, the questions tend to be very long. And so what instructors tend to do is they take a general form, they work through the general form, and then It's up to you to figure out how to apply that to a numerical example. And so I really want to help us bridge that gap here by going through some derivation and also some examples. All right. So separation of variables is one of the most widely used techniques for solving differential equations. Okay, so it is important for us to be able to recognize what is separable and what is not. Okay, and it turns out that this first differential equation, dy dx equals g of x times h of y, is a separable differential equation. It also turns out that this one, dy dx equals g of x plus h of y, is not separable. Okay. Now, what makes one of them separable and the other not? Separable basically means you can get all of the x's dx's on one side and all of the y dy's on the other side. All right, meaning that you can separate into the different variables that you have. And so if we take a look at this one boxed in the blue, let's see how we can separate that. Okay, so if we have dy dx equals g of x h of y, what is one thing I could do to start to collect the x's on one side?
We can divide. Oh, well, multiply by dx and divide by h of y.
Perfect, perfect. So this dx in the denominator, if I multiply it on both sides, it'll go away on the left side, but it'll still be there on the right-hand side. So we'll get dy equals g of x h of y dx. So that would be sort of one step. And then like Hector said, we can now divide by h of y. And so we'll get 1 over h of y dy equals g of x dx.
Is this similar to implicit differentiation? Kind of?
Not quite, because we are separating them first, and then we're actually going to integrate on both sides. Whereas implicit, we don't separate, and we use the rules together, and then we separate at the end.
Oh, okay.
Okay. All right. I do want to point out that some people like to write this as 1 over h of y dy. Other resources might write it as dy over h of y. And as simple as that change is, I just want us to recognize these two are equivalent expressions, right? So we can put the dy on the top, we can put the dy next to it. That's really up to you. Now, if we wanted to solve, we notice there are derivatives on both sides. So how do we get rid of the derivatives? Well, we integrate, right? Now, before we integrate, I'm going to rename one thing. Instead of calling this 1 over h of y, I'm going to give it a different name. I'm going to call it p of y. Okay. So p of y dy equals g of x dx. And 1 over h of y is just equivalent to p of y. Okay. And I'm writing it like that because when we divide, we end up with different things depending on what we're dividing by. So when we integrate, we want to make sure that we've got the simplified version and then applying whatever rules we need. Okay, so we've separated. Now we're going to integrate both sides. So if I integrate p of y dy and I integrate g of x dx, all right, what that will allow me to do is find a solution. Okay. Now, we could use whatever letters we want. Typically, once we've integrated, we use a capital letter. So I'm going to call the integral of P of y dy, I'm just going to call that capital H of y. So I've integrated and I got some function. On the other side, when I integrate the lowercase g of x, I'm going to say whatever that answer is, I got a capital G of x, right? So that's just notation. But one thing that I hope we remember from integration is that if there are no bounds, we better have a plus c. Okay, so if there are no bounds, we're looking at indefinite integrals, we have to have that plus c. Okay. Now, technically, though, shouldn't we have one on this side as well, right? If we're integrating both sides, we should have a c on both sides. And so I'm going to write this out a little bit differently. I'm going to write this as h of y plus c1 and g of x plus c2. Okay. So we integrate, we have a constant on both sides. But here's the thing, whether you go to Paul's online notes or any other differential equation resource, you'll never see those two constants like that. Because what people do is you're going to take that constant, you're going to combine it with the one on the other side, and we're just going to have one on the other side. So h of y equals g of x plus c. Okay. I think Paul actually has a great phrase in somewhere in his lessons. He says that we play fast and loose with the constants. All right. So fast and loose with the constants, because it's not so important what each individual one is. It's more important that we have that one after we've combined things. Okay. And honestly, that comes from just having so many other pieces that we're working with, that it's really important what that one particular constant is rather than what was it along the way at some point. Okay. So if we were to sort of summarize this, we might say that we separate first. Okay. So we see if we can separate, and then we integrate. All right, so we separate things and then we integrate them.
For the constants, although we combine them, if we were to have a second order problem, do we still differentiate between the constants?
We're going to use different techniques for a second order one. And so I think with those, what you'll find is they'll end up being two constants, because you're going to integrate once and then you're going to integrate again. And so each time you integrate, you'll end up with another c.
Okay, thanks.
Mm-hmm. All right, I see a question in the chat. We multiplied the top left equation by g of x, by d of x. Okay. So it is both a notation as well as you can treat it like a fraction. Okay, so even though we typically think of this as a unit, when we look at differentials, which is kind of a small topic in Calc 1, so not every professor gets to it, but the idea of the differential is dx really stands for the change in x, whereas dy stands for the change in y. And so we can then treat it like a fraction and multiply and manipulate that way. Okay. Now, I think it is important to sort of go back to this one in the red where I was like, it's not separable, trust me, right? But I think it's useful, maybe we walk through just a little bit of why it's hard to separate. So if I were to use the same idea that someone contributed earlier and multiply both sides by dx in this red one, we might notice that we'll get dy equals g of x plus h of y, that whole thing times dx. And so that dx actually ends up going with the g of x and the h of y. And so even though we multiplied, we didn't actually get it to a point where we can collect all of the x's on one side and all of the y's on the other. And so that plus sign turns out to be a really big difference. Plus sign means that we can't separate them. Whereas if we are multiplying the two functions, we can work with our addition, our multiplication and division to get all the terms on one side. Okay. All right. We ready to try a couple examples? Actually, work through some. All right, so I think we have 5 examples today. Each of these examples were specifically chosen to highlight some of the integration techniques that maybe are a little bit rusty in there, okay? So we'll go through a couple of them and see what shakes out. All right, so example 1, we've got 1 plus x, that quantity times dy, minus y dx equals 0. Now, I claim that this is a separable equation, all right, because it's the only technique we've learned so far, and we're in the separable one. But if you were to see this on a homework, for example, I did not tell you which one is which, right? And so it would be useful to think about, how do we know? And so one thing I tend to do first is I try separating, all right? It's sort of my go-to technique. So if I wanted to separate, maybe one thing I could do is add this y dx to the other side. Now, as soon as I've added that, I think it becomes a little bit easier to see that with some division, I can collect all of my x's, dx's on one side and all of my y dy's on the other side. In particular, I'm going to divide by y, and I'm going to divide by 1 plus x. So I'm going to get 1 over y dy equals 1 over 1 plus x dx. Right, so I divided by y and 1 plus x. Usually with a separable one, it'll be no more than like a couple steps before you're like, oh, okay, I could separate these. Okay. All right, we've separated. Now we need to integrate. So I'm going to integrate 1 over y dy, and I'm going to integrate 1 over 1 plus x dx. Okay. So what rules do we remember? Integral of 1 over y. Anyone got that one?
Is that ln(y)?
It is.
Okay.
Yay. All right. So we want to be a little bit more specific. We're going to say this is the natural log of the absolute value of y. Okay. Because when we when we take a natural log, the input can only be positive. We're not going to write our plus c here because we're going to lump that on the other side with what happens after we integrate the x part. Okay. Now, there is a rule for integration that I want to highlight with this side. Any guesses as to what that rule is? Or what technique? Yeah, there you go. So we are actually going to use u sub, okay? Now, one of the things that I want to point out is in this case, if we use u sub or if we forget, it actually doesn't matter, but that's not going to be the case most of the time. Okay, so we really want to be able to identify that. And in this case, we'll let u equal 1 plus x. Du will just equal 1 dx. And so I'm able to substitute 1 plus x. I'll substitute that with a u. And everywhere I see a dx, I'm going to substitute that with du. Okay, so we'll make a few substitutions. And because this is our first integral, let's kind of take this step by step. When we substitute, we'll get integral of 1 over u du. Okay. Now, I think it's clear that we have our natural log, all right? So natural log over here, we're also going to have a natural log over here. So natural log absolute value of y equals natural log absolute value of u. And now we can have our plus c, all right? Once we have that, we need to make sure that we put the x's back in, all right? So we don't want to forget that part. Our u sub is not complete until we get back to the form in which the question was asked. So natural log of 1 plus x plus c. All right. Now, as far as the calculus goes, we're done here, all right? And so I want to make a note that an equation in this form is called an implicit solution. And what makes it implicit is that I didn't solve for y. I didn't get y by itself, all right? We're going to find that with a lot of our questions, the answers are going to be so complicated that we're just going to leave them in implicit form, okay? I do, however, want to point out, how would we turn this into an explicit solution? In other words, how would we get y by itself, okay? So for this particular one, to get the explicit solution, good review of some algebra. How do I get that y out of the natural log?
Multiply by e.
Okay, so yes, we are going to use e. We're going to raise both. We're going to do e to the power of both sides. Okay, so if we were to write that out, it would be like e to the natural log of y equals e to the natural log of 1 plus x plus c. Okay. Love that we remember that exponentials, e's, undo the natural log. I think that's really an important concept. All right. Now, what happens here, e's and natural logs undo each other. So in effect, we only end up with this absolute value of y on the left-hand side. Now we need to be really careful about how we unpack the other side, okay? So to unpack that, we might actually need to separate our two exponents. So we'll have e to the natural log of 1 plus x times e to the c, all right? And that is because when we add our exponents, it came from two terms that had the same base that I multiplied together.
One question.
Yes.
For the, well, it's also the previous step for exams. If we were to have like a simple step, like the simple u sub, do we still have to write it into our work, or can we just skip it to save time? I don't know, like the u equals 1 plus x, and we just go from 1 over 1 plus x to the ln of 1 over 1 ln of 1 plus x.
I think you ask a really great question. I would, at least for the first couple assignments, maybe show more work than you're used to. I think it would be important that way, in case there are mistakes, we can kind of identify where the breakdown happened.
Oh, okay. And also that applies to the e to the c, because that we can just summarize it to c, right?
Exactly. And so that's what you're going to see. That's what you're going to see in a lot of answer keys. that nobody writes e to the c because e is a number and c is a number. And so what we typically do, so this will be absolute value of y. This will be absolute value of 1 plus x. And then this e to the c, we typically write as just a capital C, okay? So e to the c, and again, this goes with that playing fast and loose with our constants. We just want to know what that number is in the front. So we'll just call it c, okay? To get our explicit solution, we could say y equals plus or minus c times 1 plus x. And that would be our explicit solution. Okay. One of the reasons why I decided not to use WebAssign for this class is because WebAssign can be so picky about all the wrong things. And so you work through this problem, you get the right answer, and you type in a lowercase c, and WebAssign is going to be like, you're wrong. And that's so sad, right? So when we're working through these, most of the time, it'll be just fine to leave it in the implicit solution, okay? The higher you go in these classes anyway, we just leave it like that. I just wanted to show us a little bit about the explicit solution so that when you're looking at some answer keys and you're like, where did that C come from? Like, why isn't it e to the C? This will be a good reminder of where that came from, okay?
And for the 1 plus x, do we still leave it as have? Well, that do we just change it into parentheses instead of absolute?
So because we have the absolute values on both sides, since I got rid of it over here, I compensated for that by having that plus or minus in the front. So
Okay, so even though we did the plus and minus, it still applies to the 1 plus x, not just the y.
Exactly.
Okay.
Okay. So this is a pretty nice example of a separable differential equation. Okay. So let's go through a couple more. Let's see what happens.
Could I ask a quick question about this one?
Of course.
And I might be way off here, but this is a first order partial derivative equation, but
Yeah.
it seems like it has two answers. So isn't that a C1 and a C2? And isn't that typically for a second order partial derivative?
Okay, I see what you mean. How do I say this? Let's say, so second order, let's say that we had d squared y dx squared equals 6. Okay, so if I want to integrate one time, I end up with dy dx equals 6x plus c1, right? If I integrate again, out pops the second constant. The fact that this C1 is attached to an X and the C2 is not means I can't combine them. So it's less about like how many of them do you see, and I should have been more explicit about that, and more about how many can you combine together. So when we look at second order ones, we'll find constants that we cannot combine together. So we'll have to have two sets of initial conditions to find those values. Okay, great question. All right, well, let's take a look at example 2. Okay, so I try to use a lot of different notation because I think we see a lot depending on what resources we want. And so in this case, we have y prime equals 6y squared x. But maybe it would be easier to see that it's separable if instead of y prime, we wrote it as dy dx equals 6x squared y. Okay, so that simple change in notation makes it, I think, a little bit more visible that we can clump all the y's on one side and all the x's on the other side. Okay, so I'll give you a moment to separate that. All right, let's see what we get. Right, so I don't know that that's grammatically correct, but I divide by y squared and I times by dx, and that should allow me to separate. And when we do that, we will get dy over y squared equals 6x dx. Okay. So I multiply by dx and I divide by the y squared. Anybody out there divide by the 6 as well? Yeah, okay.
Yeah.
Yeah. I'll leave that up to you. I think conventionally, we tend to keep the constants with the x, but it doesn't matter. We'll still end up with the same answer. Okay, so it's more like when we're separating, let's not move more things than we need to, or if we're going to move them, let's move them in a way that will make it easier for us. And I think because we're integrating next, 6 as a coefficient for the x is easier to integrate. Whereas if I had a 1/6 here, now I have some fractions to deal with, which is not bad either. But I think maybe it's just, we're already going to be doing a lot. So let's kind of leave it where it is. Okay. All right. So if I'm going to integrate both sides, we'll have something like this. How do I integrate this left-hand side?
If you think of it as y raised to the -2, you can add to the exponent and multiply by the new, or divide by the new exponent.
There you go. I would 100% take the time to rewrite this. Okay. Common mistake. The integral of this is not the natural log of y squared. Okay, that is probably the #1 mistake I see. And I just want to really highlight that here, that you should 9 times out of 10 use that power rule. The only time you don't use the power rule is when that power is a -1. Okay. William, you ask a great question. What if y equals 0? And so if you read in the text, they'll talk about something called an interval. And so by interval, they mean like, where can we actually have solutions? Because there will be points where it might be undefined, and that would be important to consider. And right now we're just focusing on like the bigger process of things and like the decision-making and the techniques, okay? But that's a really excellent question that you bring up. All right, so we integrate, let's see what we get. We'll get negative y to the -1 equals 3x squared plus c. So I've already taken the plus c from this side and combined it with the one on the other side. And if I wrote this as -1 over y equals 3x squared plus c, then we could say this is our implicit solution. Okay. So we separated, we integrated, we got an implicit solution, and it would be absolutely fine to leave it in that implicit solution. Okay.
Wouldn't this be also explicit since we separated y?
That's a great question. So explicit actually means you have to have y equals, not
Oh, okay, I see.
-1 over y. Does that make sense?
Yeah, we
Yeah.
just, yeah.
So that's why this one, we got y equals, is considered an explicit solution. Okay. Any other questions on example 2 or 1?
It's totally okay to leave this implicit.
Yeah.
This is a pretty easy one to.
Yeah, you could just, multiply by -1, flip those, that would also be okay. All right. Any other questions about 1 or 2? All right. Let's try example 3. All right. Zoom in a little bit here. I don't know how old your eyes are, but I feel like my vision's gotten significantly worse in the last year, staring at a screen all the time. So for example 3, we have dy dx equals, and then sort of a gross looking fraction thing. And again, I know that we're in the separable section, but out of context, separating is always a good thing to try first. And in this case, I think if we do a little bit of cross multiplication, we'll be able to get all of the x's dx's on one side, all of the y dy's on the other side. And so we'll get 2y minus 4 dy equals 3x squared plus 4x minus 4 dx. All right, so that's just with a little bit of cross multiplication. We've gotten rid of our fractions and we've collected all of our quote unquote like terms on each side. All right, once we've separated, let's integrate. Well, this one's not so bad. Everything is positive powers, right? So we don't have any sort of exceptions to that power rule. All right, so if we integrate 2y, we'll get y squared. If we integrate 4, we'll get 4y. We're going to keep that constant. We're going to save it for the x side. And when we integrate the right-hand side, we get x cubed plus 2x squared minus 4x plus c. Okay. So this would be my general solution, all right? Now, let's suppose that I gave you further directions and I said, now I want you to find C. How many initial conditions do I need to give you? I see one answer for 2. I need 2 initial conditions, 3 initial conditions. All right. So it turns out I have 1 plus C. There's only one thing I need to solve for. We only need 1 initial condition, okay? The other way we could have known dy dx is a first order differential equation. First order means you need 1 initial condition to solve, okay? So let's make up an initial condition. Suppose that y of 1 equals 3. Okay, so that's the initial condition I'm giving you. Y of 1 equals 3. We're going to take the 1, we're going to plug that in everywhere we see an x. We're going to take the 3, we're going to plug that in everywhere we see a y. And then the only thing we won't know is c, so we'll be able to find out a value for that constant. So 3 squared minus 4 times 3 equals 1 cubed plus 2 times 1 squared minus 4 times 1 plus c. I believe the left-hand side becomes -3. And the right-hand side, let's see, 1 plus 2 is 3. 3 minus 4 is -1 plus c. And we're going to add 1 to both sides. We get c equals -2. And so all we need to do is put that -2 into here, and we will have our solution for that initial value problem. Okay, so y squared minus 4y equals x cubed plus 2x squared minus 4x minus 2. And this would be our solution to the initial value problem. Okay. So a general solution over here on the left, and then the one boxed off on the right-hand side, that gives us the solution for an initial value problem, right? So first order means I'm going to give you one initial condition. Second order means I would give you two. Any guesses to how many I would have to give you for a third order differential equation? $42. I hope not. I hope not. That would be so sad. And yes, this general solution would be considered implicit. Okay, so this is an implicit solution. Right. And so just to make sure we're all okay with this is the order. So this is how many initial conditions I would give you. A third order, I would give you 3 initial conditions. Okay.
Is it correct to say that an in order differential equation requires n number initial conditions?
Exactly. Okay. All right. So we've got 2 more examples to go. Again, we're going to try and highlight some of these common integration techniques here. So we've done some power rule, we've done the natural log, we've done U sub. Ooh, so many letters. I hope this sparks some joy. But with so many letters, we still want to see if we can collect all of the x dx's on one side, all of the y dy's on the other side. And so what are your thoughts on what I should divide by or multiply here? Maybe we could put those thoughts into the chat.
Well, we can pass dx by multiplying to sine 2x and then dividing by cosine x.
All right.
And we can have ey divide into the left side.
So we're going to move the dx and the cosine x to the other side. And then the e to the y, yeah, we're going to divide by that. So divide by e to the y. Okay. Now you don't have to write these down, but I think sometimes when you're going back to your notes, it's useful to be like, how did somebody just get here, right? So knowing that if we divide by cosine x and e to the y, let's maybe take this step by step. We get e to the 2y minus y. I'm going to move the x's first, so I'll keep this dy, but on the other side, I'll have e to the y sine 2x over cosine x dx. And then we're going to divide by that e to the y, so we'll get e to the 2y minus y over e to the y dy equals sine 2x over cosine x dx. Okay. So let me just kind of pause here for a moment. How are we feeling with the separation part? Feeling okay? Okay. All right. Now we need to integrate. Before we integrate, it might be very beneficial to see if we can use algebra to simplify some things. Okay. So that's what we're going to do. I could write e to the 2y minus y over e to the y. I can split that into two fractions. Specifically, e to the 2y over e to the y minus y over e to the y. Okay, this is a very helpful trick. Split into as many fractions as you have numerator terms. Okay. We'll simplify that in a little bit, but I just want to make sure we're okay with the split. The second side I don't know how long ago this was for you all, but there's another way of writing sine 2x. And yeah, 2 sine x cosine x. Perfect. Okay, so this is a common substitution, our double angle formula here. Okay, and what makes it really nice is we can see that some things are already going to cancel. The cosine and the cosine, I'm not going to have any fractions on that side anymore. That will make my life much easier when I'm integrating. But if we come back to the left-hand side, let's simplify that even more. Okay, so what does this first term become? This e to the 2y over e to the y. Good, that's going to become e to the y, all right? And William, to your question, I think this is the most common one that comes up, 2 sine x cosine x, so that's a good one to know. The other ones come up a little bit less frequently, but if you're going to choose one, I would say the sine double angle is a good one to know. Okay. Let's rewrite the second term here as well. We'll get negative y e to the negative y. Okay. So I think we're fine integrating the right-hand side. I think we are fine integrating e to the y. I bet it's been a while since we integrated something like that second term though, right? This second term, we are going to need integration by parts. Okay, we're going to need integration by parts to do that middle term over there. All right, so integration by parts is really the integral equivalent of product rule for derivative. Okay, so integration by parts is really the integral equivalent of product rule that you learned for derivatives. Okay, so anytime you see a product, you're going to need some sort of special rule to find that derivative or that integral. Okay. Anybody happen to remember the integration by parts formula? It's okay if you don't. We'll make
UV minus VDU.
Yeah, there you go. There you go. Okay, so the integral of integration by parts, integral of u dv is going to equal uv minus the integral of v du. Okay, so good formula to know, integration by parts. If this sounds very unfamiliar, I would check out Paul's online notes. He does a great job, or maybe watch some videos about integration by parts. Okay. Some people remember the formula and then they're like, but I don't know how to choose which one is my u and which one is my dv. And that really is the part that makes us successful. Okay. So in general, I think about it like a hierarchy. I prefer the phrase LIPET, but L stands for any sort of log. I stands for some sort of inverse, like an inverse of a function. P stands for a polynomial. E stands for exponential, and T stands for trig. All right, so LIPET. There's also another one that's Li8, but same sort of idea, that there's an order in which you prioritize what is going to be the U and what is going to be the DV, okay? And so in this case, we're gonna let U equal Y, because Y is considered a polynomial, whereas e to the negative y is considered the exponential. Okay, so the one that comes first in this list is going to be your u. So we'll let u equal y. That means dv equals e to the negative y. Now, in order to use our integration by parts formula, we need to find du and we need to find v. And so since our u is y, our dv is, or du is just 1. And what did I take a derivative of to get e to the negative y?
Isn't it the same thing, like e to negative y? No?
Almost, except we got to compensate for that
Oh, yeah.
negative sign, right? So it's going to be
So
negative
y.
e to the negative
Okay.
y. Okay. Now, this is a good example of u sub, where we're not going to write out the u sub, but there was a u sub that happened, which is how we got this negative sign in the front. Okay. All right. We're going to go back up to the top of this section and we will write out the entire left side with that integration by parts for the second term. And then we'll also take a look at that right-hand side. All right, so integral of e to the y is just going to give me e to the y minus my integration by parts. Let's see, we have u equals y. So uv will be these two multiplied together. So negative y e to the y. So uv minus the integral of v du. So v is negative e to the negative y, and du is just 1. So we'll get negative e to the negative y dy. That is the left-hand side. And the integral of 2 sine x is negative 2 cosine x plus c. All right, let me pause there for a moment. That's a lot of writing. It's a lot of synthesizing. Are there any questions so far about this particular setup? Yes, that should be. Sorry, there is a negative sign here. I'm talking too much and not paying attention to what I'm writing. But yes, that is negative y e to the negative y. All right. Now at this point, we need to finish up the left-hand side, right? And so we just want to be really careful about our signs here. We've got e to the y plus y e to the negative y. Ooh, lots of minuses here. Minus, minus, minus is going to give us negative integral of e to the negative y dy. And when we integrate this, we're going to need a little mini u sub here. And that all that will do is change the sign of the answer. We'll get e to the y plus y e to the negative y plus e to the negative y equals negative 2 cosine x plus c. Okay. Now I think we can tell just by how much work we've done and looking at our final answer, it is 100% fine to leave this as an implicit solution, right? You got this far, you remembered your integration by parts and all those mini u subs along the way. I don't need you to show me you can solve for y, right? We just kind of leave it like that. And it'll actually be easier when we try and solve for c if we leave it in this format, okay? So let me zoom in so you could see all of it on one page. Are there any questions so far on example 4? Because this is like the most calculus we've seen so far. All right. So we've got about 10 minutes left. And I think we've got just enough time to start and hopefully finish example number 5. Okay. So any guesses as to what technique I'm going to be highlighting in example number 5? Yeah.
Inverse trig, maybe?
That partial fractions, we're going to be using partial fractions quite a bit towards the second half of our summer session. Okay, so partial fraction decomposition is the skill we'll be highlighting in this particular problem. Okay, so let's see if it's separable first. And in order to see that, maybe we write it as dy dx instead of y prime. And we get something like this. We can multiply both sides by dx. We can divide both sides by y squared minus 1. Now, since we've collected all those like terms, let's go ahead and integrate. So the integral of 1 over y squared minus 1 dy equals the integral of 1/2 dx. Now this right-hand side, I feel like we can integrate that fairly quickly. That'll just be 1/2 x plus c. But where we really need to do the work is how do we integrate that one, okay? And so we're going to start by splitting this into two factors in the denominator. So we'll end up with 1 over y plus 1 times y minus 1. And in order to integrate something like this, it would really be beneficial if we could write it as something over y plus 1 dy plus something else over y minus 1 dy. And so that's what I mean by partial fraction decomposition. We're taking one fraction and we're splitting it into multiple fractions. And we just have to figure out what those numerators are to make that 1 on the top over there. Okay. All right, so how do we find partial fractions? Let's write this down here. Okay, so in essence, what we have is a problem that looks like this. 1 over y plus 1 times y minus 1 equals, we typically call this like some sort of capital letter plus a different capital letter. All right, and our goal is to find out what these capital letters are. And one of the things you might remember way back from pre-calculus is that as long as you can get a common denominator on both sides, you can effectively only work with the numerator. And so our goal here is really to think about how do we create a common denominator on both sides, ideally the lowest common denominator. Okay. So if I copy and paste this real quick, and then take this, scooch that over a little bit. What do I need to multiply the first fraction by to get the same denominator as the other side? Well, y minus 1, but we don't want to change the problem, so it's going to be y minus 1 over y minus 1. What will we multiply the second fraction by?
Y plus 1.
Yeah, y plus 1 over y plus 1. Okay. Now, since the denominators are the same on both sides, I can get rid of those and focus on what's happening in the numerator. So we have 1 equals a times y minus 1 plus b times y plus 1. Now we got to find a and we got to find b. Okay. I'm going to show you a longer technique right now, but I'll show you a shortcut once we get deeper into partial fractions, okay? So the long way to do this is you're going to distribute and you're going to create a system of equations that has, based on how many letters they have. So 1 equals ay minus a plus by plus b. And maybe it would be helpful if I wrote a 0y plus 1 on the other side. The reason that might be helpful is it might be easier to see the sort of like terms that I'm going to collect. 0y is going to equal ay plus by. Those are all considered like terms because they have y's. And then 1 equals negative a plus b. And we can group those into two equations. So we'll get 0 equals a plus b, and 1 equals negative a plus b. You can solve this system however you wish, substitution, elimination. I tend to like elimination, especially if it has the same coefficients. So if I add these two equations together, I'll get 1 equals 2b, or b equals 1/2. Now I just have to figure out what A equals. I can plug it into either one of the other equations and I'll find A also equals 1/2. Now they won't always be the same. And actually, yes, they won't always be the same. And actually they're not, right? This should be a negative 1/2. But it would be valuable to know how to set up that system of equations to get to the coefficients that you want, okay? So we've got B equals 1/2, A equals negative 1/2. Now we can put those back in to those coefficients right up here. All right, so on top of the first one, we're going to put negative 1/2. And on top of the second one, we're going to put the positive 1/2. Negative 1/2, positive 1/2. Let's bring this back up here. All right, now we actually get to integrate, okay? Negative 1/2, the integral of 1 over y plus 1 dy, plus 1/2, the integral of 1 over y minus 1 dy, equals 1/2 x plus c. Now, I don't really like all the fractions here, so I'm going to go ahead and multiply both sides of the equation by 2. And check out what we get. Negative integral of 1 over y plus 1 dy plus 1 over y minus 1 dy equals x plus c. I don't even need to write 2c because it doesn't matter along the way what it is. It matters at the end what the c value is. All right. Last 30 seconds here, we're going to integrate both of these. Turns out it is a u sub situation. And we're going to be able to use that natural log because it's 1 over u. So that plus the natural log of y minus 1 in absolute value equals x plus c. This would be an absolutely fine implicit solution. Okay, this would be an absolutely fine implicit solution. You may see an answer that looks like this. And all that happened is we did the log properties. So I don't know if you remember those log properties from way back when, but when you have natural log of, let's say, x minus natural log of y, it's the same as natural log of x over y, right? So sometimes that is sort of a streamlined way to simplify that. However, this line before that is absolutely fine. Okay.
Professor, just to go back real quick, so the 1/2,
yeah,
up top. So basically, it got thrown and were combined into the c, the constant. That's what happened. Okay, so that's why. Okay, got you.
Mm-hmm.
Professor Judy, is it okay to have the 2c at the end, or would you prefer not to put that in?
Usually, if you're multiplying anything into that c, we just keep absorbing it. That way, at the end, we'll have just a c.
Okay, would it be wrong if it was to say 2c?
It's not wrong, but you might never meet someone else in the field of differential equations who does it that way.
Okay.
Okay, so like when you're reading answer keys and stuff, no one will write the 2c, they'll just write a c.
Thank you.
You're welcome. All right, folks, I know we are officially over time, but I will post the video. I will post the notes for this. I would get a head start on that homework that's due later this week. See if you can find all the questions that are the separable ones. Knock those out of the way today. Okay, so find all the ones that are separable, get those done. And that way, when we learn a new thing tomorrow, you'll be able to go back and see, oh, which ones are that technique. Okay. All right, folks, I'll see you later. Have a great rest of your day.